Hi everybody, this is Mustafa Kalami from Yarpus, and in this video tutorial we are going to learn how to solve and implement linear programming problems in MATLAB. The general form of the linear programming problem is as follows. We'd like to minimize or maximize the value of an objective function, which is a linear combination of our decision variables. For example, if we have decision variables named x1, x2, and x3, then we'd like to maximize, for example, x1 plus 2 times x2 minus x3. And this is a linear combination of our decision variables, and so our objective function is linear. We'd like to maximize this value, find the maximum amount of this objective function subject to some constraints. For example, we must ensure that x1 plus x2 is less than 5, for example. For another example, we must find x1, x2, and x3 in a way that x1 minus 2x2 plus 3x3 is less than 10, and some other conditions like this. So we have an objective function and we have a set of constraints, and the general structure of these constraints and our objective function is linear. Everywhere you have linear combination of decision variables. Also, it is possible to have some equality constraints. I write down another constraint, which is equality constraint, and for example, x1 plus x3 must exactly equal to 8. And this is a linear programming problem. The general form can be expressed as, for example, maximizing some vector transposed times to a vector which contains our decision variables. F is a vector with the same size as our decision variables vector, and it is the vectorized version of these equations, and it is in general form. And subject to that, we have some inequality constraints. For example, a matrix times our decision variables less than or equal to some vector b, or a prime times x exactly equal to b prime. This system of inequalities represent our inequality constraints, and this system of equations represent our equality constraints. So we have both type of constraints here, and sometimes we have some lower bounds and upper bounds constraints, which is represented as follows. X is at least equal to LB, lower bound, and must be less than or equal to upper bound. And these are lower bounds and upper bounds of our decision variables. And this is the general form of linear programming problem. So this is linear programming general form. Now we are going to solve this problem using MATLAB functionalities, built-in functionalities, and there are several approaches to do this, and there are several algorithms to solve linear programming models. However, the implementation is quite same. Let's start with the implementation of our model. First of all, we need a simple problem to start with, and for example, we would like to maximize 5 times x1 plus 6 times x2, subject to that we have x1 plus x2 less than or equal to 10, and x1 minus x2 is greater than or equal to 3, and 5x1 plus 4 times x2 is less than or equal to 35, and both x1 and x2 are non-negative numbers. And this is our test problem. If we'd like to find these matrices F, A, B, A prime, B prime, LB, and UB, we can do this here. I shift these equations to the left and let's define our matrices. For example, F is as follows: 5 and 6. This is our coefficients in the objective function. And all of our constraints are in the inequality form. And we don't have any equality constraints, so A prime is empty and B prime is to an empty matrix, and A equals to 1, 1, 1, 1. And note to the direction of this inequality, and this must be converted to the form of smaller than or equal to something. And we should rewrite this as x minus x1 plus x2 less than or equal to minus 3. And this is the general form we accept for the matrix form of our linear programming model. So the second equation is modeled with -1 and 1, and the third equation is formulated with 5 and 4 as coefficients, and the right-hand side of our inequalities is given by 10, -3, and 35. And our lower bounds are 0 and 0. And we don't have any upper bounds, and it's not specified. So we have all matrices which define exactly our linear programming model. And in the implementation of our problem in MATLAB, we need these matrices. And we've done this here just because we learn how to form matrices needed to implement our linear programming models in MATLAB. Okay, now we're ready to implement our model in MATLAB, and let's define our matrices. F equals to 5 and 6. You can define it as a vertical or horizontal vector. They are quite same, and we choose here to define coefficients of objective function as a horizontal vector. And F equals to 5 and 6, and A and B equals to, let's define this as A1, 1, 1, and in the next row we have -1 and 1, and in the next row we have 5 and 4, and B equals to 10, -3, and 35. We can transpose it to have column vector. And now we don't have any A prime or A equality or B equality, and we have just a lower bound vector remained, and let's define the lower bound as 0 and 0. Not differ that you define this as a row vector or column vector, and they're same. And what function we should call? It's the linprog function. Let's see the documentation, linprog. And this states that we are going to solve this objective function but minimizing that value. So to solve our maximization problem, we should negate and multiply the coefficients matrix with -1 to get the problem as a maximization problem. Just because the linprog solves only the minimization problems. And other parts of the linear programming problem is same as our definitions, and it accepts if A, B, A equal, B equal, that we referred to them as A prime and B prime. And after that, we provide a lower bound and upper bound and some options. Let's call the linprog function linprog and F, and remember to negate the F because our problem was maximizing, and linprog accepts and solves minimization problems. And A and B, and we don't have any A equality and B equality, and we just have the lower bound, and we just ignore all other inputs. Okay, let's have the problem solved. The problem is solved, and the x1 is 5.2222 to the infinity, and the second variable is 2.2222 to the infinity. And if you see the documentation again, the f value, the function value of the optimum solution found, is written as the second value, and you can get it with xopt and fval and linprog minus f a b empty and lower bound. And we now have the optimum value of x and the related objective value, and this is the actual objective value, 39.444, and this negative sign is due to the negation of our coefficients. So the optimum solution is represented by xopt, and the related objective value is this. Let's gather these definitions and this into a script. Let's create a function and let's define problem. F is, for example, -5, -6. The constraints are represented by 1, 1, and in the next line we have -1 and 1, and in the next line we have 5 and 4, and the right hand side of our inequality constraints 10, -3, and 35. These are our right hand side equations. A equality is empty, B equality is just empty, lower bounds are 0 and 0, and upper bounds are empty too. And solve the LP problem, and we call the linprog function, and the function returns the optimum value of decision variables as xopt. You can name it whatever you want, and xopt and the value of function for this optimum point, optimum solution, and linprog, which solves -f due to the difference between our problem and the minimization behavior of linprog function, and A and B and A equal and B equal and lower bound and upper bound. And suppress this semicolon to have the outputs. Let's define as app1, and let's run the program, and for example app1, and the x-optimum is here. I think sorry, we defined the minus here, and this is not needed anymore. Let's run. Okay, that's true, and it is the optimum solution of this problem. Now suppose that we are going to solve a well-known linear programming problem known as transportation problem, and we are going to create the matrices, these matrices, automatically using MATLAB program. This is just an example to know how to use MATLAB scripts to define needed matrices automatically. What's the transportation problem? We are going to solve a transportation problem. It is a linear programming problem, and it assumes that there are some producers or warehouses or other things, they're providers, and I write here providers, and some consumers or customers. And for example, we have 2 providers here and 3 consumers here, and they are shipping some products, services, or other things to consumers, to all of consumers, and this is the provider number 1, the provider number 2, and this is the consumer number 1, number 2, and number 3, and this is the amount of shipment from provider number 1, the first provider, to the first consumer. And this is x12, x13, and x21, and x22, and x23. We have 6 unknown variables, and we know that the cost of this transportation is defined by some coefficients, some parameters like C11 and C12, C21, and etc. And we know that all the cost of shipment for all of these routes. I write the parameters for other routes. So we can compute the total shipment cost as this. The cost Z equals to C11 times X11 plus C12 and etc. So this is our transportation cost, and we are going to minimize this amount. However, there are some production capacities here and some demands here, and we must remain in the feasible bounds of our production capacity, and we must meet the demands and requirements of our consumers. So, for example, let's shift this equation to up. For example, this consumer needs 500 items, this needs 600 items, and this needs 300 items, and the production level of this is 900 items, and this is 800 items. So the amount of outputs from a provider must be less than or equal to its production capacity, and the inputs of any consumer must be greater than or equal to its demand. And we can write these equations. Write the production requirement here, and x11 plus x12 plus x13 must be less than or equal to 900. And for the second provider or producer, we have this. And for the consumers, we must meet their requirements, and x11 plus x21 must be greater than or equal to 500, and x12 plus x22 must be at least 600, and x13 and x23 must be at least 300. So we are going to minimize this transportation cost. We must satisfy the production capacity of our providers or producers, and we must meet demands and requirements of our consumers. And we know that all of these values are non-negative values. So xij for all I and j's must be at least equal to 0. And this is our transportation problem. We wrote down a sample and we converted it to a linear programming, and now we are going to solve this problem. But we are going to create a function, a script, which accepts these values, transportation costs, as a matrix, and these production capacities and these demands. We just need a vector of production capacities, a vector of demands, and a matrix of shipment costs. And let's define the function, and the function will return the matrices needed to define the linear programming problem, as linprog needs. Let's create a function which returns the problem. For example, let's name it as LP, linear programming problem, LPP, and transportation problem, or for example, transportation problem with some shipment costs, some cost values, some production capacities, and some demands. And we know that the general form of this C is that we have two rows, C1, 1, C2, 2, two rows and three columns. And we have a matrix C that have rows equal to the number of providers and have columns equal to the number of consumers. So if we are going to calculate the number of providers, NP, it is the size of C and number of rows. We are calling the size on C with the second parameter 1, which returns the number of rows of matrix C. And number of consumers is the size of C, but in the second dimension, which returns the number of columns of the matrix C. And this NP must be equal to the number of elements in this vector, and this NC must be equal to the number of elements in this vector. Now we are going to define all of matrices we need. We need F, A, B, A equal, which is not needed here, but just because we don't have any equality constraints, and just we need the LB, lower bound. And finally, the F is equals to this C, which is flattened. You know that if you want to flatten a matrix, for example, this is our matrix, you can flatten this in this way. And this is the matrix C flattened. And let's form the inequality constraints related to the production capacities. The production capacities are in the form of this, and you see that this is a matrix with all numbers equal to 1 here and 1 here. But all of decision variables does not appear in this and this equation and all other equations. Let's unify the equations using our variables. If you flatten a matrix, for example, you see that you flattened the matrix C, and this is the first one, second, third, and you see that the first, second, and third are presented in this way. So if this is the x1, 1, it is here, and it is the x2, 1, and this is here. So our variables after flattening are in this order: x1, 1, x2, 1, x1, 2, x2, 2, x1, 3, x2, 3. This is just for the simplicity. And if you have the other problem, this order will change. For this specific case, the order of variables in final vector is as represented here. So let's define this x11 plus x12 plus x13 less than or equal to 900. If you'd like to represent this using this notation, know this as a vector of decision variables, you see that this is a column vector. You can define this as 1, 0, 1, 0, 1, 0 times x is less than or equal to 900. You see that we have 6 decision variables and 3 of them appeared here. The second one, x21 plus x22 plus x23 less than or equal to 800, this will be as this. And if we unify these matrices, we will have 1 0 1 0 1 0, create some space here, and the second row. This is our matrix A, and B is equal to 900 and 800. So you see that for some values we have 1, and for some other values we have zeros. And we need a mechanism to find the index of, for example, x11 in this sequence. And we have functions in MATLAB which do this calculation. For example, one of them is sub2ind, and this converts some sub-indices to singular index. For example, sub2ind accepts the size of matrix, 2 rows and 3 columns, row sub and column sub. We'd like to find the position of first provider to second consumer, the position of variable x12, and it says that it is the third one, and you see that it is the third. And let's check the 1 2 3. 1 2 3 is 5. 2 3, it's the 6th, and 2 2, it's the 4th, and this works as well. So with this function we can find related indices and fill the related indices with ones, and we just repeat this for all providers and all consumers. For providers, this is their production capacity, and for the consumers, this is the demand and the requirement. Okay, let's define an inline function which performs these calculations a little simpler. For example, let's define ind as a function of I and j, which returns sub2ind for size of this matrix C, and row sub is I and the column sub is j. This calls every time the function with a simpler form. You just need to, for example, ind 2 to 3, and this does the job completely in a simple form. Okay, this is our f, and let's define the matrix A as A empty and B empty, and for every provider here, NP number of providers, and for every consumer here, the coefficients for this one is, for example, is zeros of size. For all number of variables, we can calculate this as number of elements in C. And this has 1 row and nx columns. Okay, and it must be out of inner for loop. And let's set the value of A for int I and j equal to 1, and this forms a single row in matrix A. And so we append this row to our matrix, and let's append the production level for this provider to our B vector. This is not a good idea to append. Next time I will improve the coding. Just for now, accept this. Now we are going to return all of matrices and other entities as a structure. For example, number of providers is NP, number of consumers, number of variables and the size of final variables, and lpp.f equals to f, and lpp.a equals to a, and lpp.b equals to b. And next time we'll add the demand constraints to these matrices too, and we'll create LB. But for now, we call this to see how will our final output will look like. Okay, for example, let's define a matrix as 1, 2, 3, 1, 3, 4, and production level equals to 900 and 800, and the demands as 500, 600, and 300. And now we are going to create a transportation problem. We need to save this transportation problem using C, P, and D. Okay, this says that we have 2 providers. It's correct. 3 consumers, 6 decision variables, and the final decision variables should be in this shape. And we have lpp.f and we have lpp.a. You see that it is exactly what we want, and lpp.b. So let's add other constraints to our code. This time we'll do this for every consumer, and let's create an empty row, and for every consumer, every provider, we must set to 1 the related indices, and now we will add the related row and the related demand level for this consumer. So this is our production capacities constraints for and constraints for consumer demands, and this is our objective function. And now we just need to define lower bounds. Let's move this index converter, and we initialize A and B. Let's simplify it. Now lower bounds are given by LB equals to zeros, the same size as F, or for example 1 rows and nx columns, or nx rows and 1 column. And this is our lower bounds, lpp.lb. And if you like to get rid of these warnings for large problems, this can reduce the speed of program. You can initialize A and B to some matrices, for example zeros. It has np plus nc rows and nx columns, and this has np plus nc rows and 1 column, because we have np constraints for production capacities and nc constraints for consumer demands, and we have nx decision variables, and the right hand side of our inequality constraints are scalars. And now we must use some counters, for example c equal to 0, and here we must increase c and the 3rd row of our matrix, and A in the row number c and in the column indicated by this index equals to 1, and we don't need this, and we don't need this too. And the B, the index c equals to pi. It makes the program faster, and it is a good idea to pre-allocate all of our matrices. And we just need to increment the counter here as well, and A for this row and the related index, and we don't need this, and the B number C is DJ. And if you run call the function, you'll see that lpp.a will give you 2 production capacity constraints and 3 consumer demand constraints, and lpp.b equals to our production capacity amount, and this is our demands. However, note to the direction of our constraints, we must negate these equations. So let's negate this, a minus 1 and minus d. This is the correct way of doing this. Let's recall the function and lpp.a. You can augment these to see both of them in single screen. Sum of this must be less than 900. Sum of this must be less than this. And for these, sum of this and this must be greater than 500 positive, or the negative sum of these variables times by minus 1 equals to minus 500. And we're done. We have all matrices, all things we need to solve this problem. Okay, let's solve the problem as well, just here. And we can define function, define the problem here. Define problem. Costs are 1, 2, 3, and 2, 3, and 1, 2, 4, and 1. And production capacities are 900 and 800, and demands are defined by 500, 600, and 300, and shipment costs, and this is the production capacities, and consumer demands form the LPP, linear programming problem, and LPP equals to transportation problem, C, P, and D. And let's solve the problem. Xopt and fval equals to linprog, linear programming, lpp.f, lpp.a, lpp.b. We don't have any equality constraints, and lpp.lb, lower bound. All of matrices are gathered into this structure, and we call linprog using this. And now let's run the algorithm, let's run the program, and we have, let's clear the workspace and run the app tool, and we have xopt as this. And we must reshape xopt to lpp.size, I think, and this reformats the solution into our matrix form, and we do this here. Xopt equals to reshape xopt to lpp.s, and lpp.s is the size of our matrix 2 and 3, our cost matrix. And this reshape converts back the flattened solution vector to the matrix form. Okay, let's rerun the program, and xopt is as here, and you see that all of demands for the second consumer is provided by first provider, and all of demand for the third consumer is provided by second provider, and both providers cooperate to meet demands for first consumer. And if you sum this X opt, you see that the demand requirements are met, 500, 600, and 300. You can see that it is equal to our demand requirements. And if you sum X opt, but in the second dimension, it is equals to 900 and 500, and our production capacity was 900 and 800. And you see that first provider will use all of its capacity, but for this second provider, 5 of 8 of its capacity is used. And that's because of the higher average transportation cost for the second provider. If you lower this, then you'll see that all of capacity for the second provider will be used. Let's try it out. I change this value and you see that X opt will be as this, and if you sum this to find the used capacity level, you see that this time the second provider, for overall lower transportation costs, will be used fully, and the first provider will not use its whole capacity. Okay, let's return this value to its original, and okay, now we've done and we created a function which automatically creates needed matrices as the form linprog functional of MATLAB needs. For other problems, you just need to write similar functions and get these matrices and then pass the matrices to linprog and get the solution, and remember to reshape or reformat the solution. Sometimes you need to separate variables with several names, for example x, y, z, or other names in different shapes and different formats. Okay, hope this was helpful for you. We'll wait for your feedbacks, comments, or probable questions. Let's have your opinion or comments on yarpus.com or our YouTube channel. Thank you very much and good luck.